All right. Hi, everybody. Sorry for being a couple minutes late today, but we can get started now. So I hope you all had a good holiday weekend, even if it was a little different this year. Um, Hopefully you got to see some people over the computer or whatever. So we're getting toward the end of class here. A couple more weeks to go, and we're going to. I think this is kind of the most fun part of the semester, content-wise, because we're going to be using all of the chemical concepts we've already talked about and then applying them to biological molecules, biological systems, which is usually interesting because it's stuff you've heard of or stuff that is directly related to what you plan to do in the future. So, um, with that said, let's get started. So behind me, I've got the carbohydrates handout. And today we're going to look at a concept that can be a little bit difficult, especially when you first encounter it. So we're going to go through it a little bit slowly, and hopefully it'll make sense eventually. And we're looking at something called chirality, and chirality is a function of or a way of describing a certain three-dimensional orientation that makes it somewhat asymmetric. And the best example of this, I think, or the easiest one before we get into the molecule stuff, if you jump to the second page, you see hands, pictures of hands. And hands are what we call chiral objects. And that's because they are mirror images that are not superimposable, meaning if you take your two hands, you can they look pretty similar, and each one has a counterpart on the other, but they aren't exactly the same. There's something three-dimensionally about them that makes them different. And when we apply that to molecules, well, anything really, when we talked about isomers, we talked about molecules that were where the atoms were connected in different ways. And we said, oh yeah, so like if you have all 6 carbons connected in a line, that was one isomer. If you have 5 carbons and then there's one coming off the middle, that's a different isomer because of the different connectivity. Now we're going to get a little bit more subtle with that and say, okay, well, we can have molecules that are actually connected in the exact same way, but are still different because of this handedness, this three-dimensional orientation. Your fingers on your hands, both hands are connected in the exact same way, right? You've got your fingers in the same order, all of that. But there's still something about those hands that makes them not identical. There's an asymmetry there that they can't be superimposed, that is, put on top of each other and have everything correspond exactly the same. So that's what we talk about when we talk about chirality or handedness. So let's go back and look at molecules and see how that kind of manifests. So again, this works better if we have actual physical models that we can play with. You may have those at home. If you do, great. You should try to put this together. If not, don't worry about it. If you can make something maybe with like some toothpicks and a marshmallow or something like that, or several marshmallows, that might also be a nice way of visualizing this if you don't have actual molecular model kits. But this is a good diagram anyway. So take a look at this one on the left. We've got a carbon that has 4 different atoms attached to it, H, Cl, I, and Br. And I'm going to be referring to the colors here, but if you can't see the colors, the top one, the H, is red, the Cl on the right is black, the I in front here is blue, and the Br to the left and back is green. Let's also remember or refresh our memory on how we express that tetrahedral geometry. We've got 2 bonds that are shown directly in the plane of the screen here, or paper. And then this wedged one means it's coming out toward you, and the dashed one means it's going back behind. All right, so we put 4 different things on this carbon, and then we also make its mirror image. Now, looking at those 2 molecules, You can see how if this was a mirror here, so it's like this molecule is looking in the mirror to this one. So each one corresponds. And you can see it's very much like putting your two hands next to each other. It looks like, from first glance, it looks like these are actually the same molecule. That everything's, from the definitions we talked about with isomers, those look pretty much the same because everything's connected in the same way. But if we then take this first one and we rotate it around so that we are now attempting to place it directly on top of this one, lining everything up. So we want the H and the Cl to be in the same place, which means the I is going to flip around to the back and the Br is going to flip around to the front. So that's what's shown right here. We're just doing a 180-degree rotation there. 120-degree rotation. And then, no, I was right before. 180-degree rotation, yes. So the Cl comes around to the other side. The H and the Cl then line up, but then you notice that the I and the Br do not. So when you turn this A around and try to put it on top of B, they don't exactly line up. And that makes them non-superimposable or non-identical. Those are not the same molecule. Those are different molecules. Even though the pieces they have are the same, they're actually different molecules. And so one of the keys for finding that and for looking at that is to look for carbon atoms that have 4 different types of things attached to it. Notice what happens if instead of having a Br and an I, we have 2 I's, 2 iodines attached. Now, when we turn this one around, we do actually have the exact same molecule. So we would say that this one is actually achiral, not chiral, because it is the same, its mirror image is the same. So those are not stereoisomers, those are identical. Those are the same thing. And this is a little bit tricky to see. Another way you can do this if you don't have models to play with is click on these links to go to this website, and you can play with some of the rotation online so you can kind of see it for yourself. When I first learned this stuff, I didn't get it at all. And it really took playing with it myself and kind of convincing myself that that was true to really make it make sense. Yeah, so good question, Jennifer. Why doesn't this line up exactly? It looks like it should. But if you physically have this model and you turn it around, you don't have the same thing. These atoms are not in the same place. The I or the one of them is going back and one of them is coming forward. So they're actually in a different spot. Let me see if I can pull up this website. I don't know if it's going to work properly over the video, but I encourage you to go to it and just try it so that you can see how this works specifically. Let's see how I can do this. Okay, so here's one of the links from that. So you've got a couple different molecules here. Don't worry so much about the R and the S designation yet. We'll get into that. But just focus on that carbon that is labeled. You can see this thing here is the CN or the NC, and then this red one is the OH. And you can see from the position there that the CN or NC is coming out toward us, and the OH is going back when the carbon chain kind of has this position, going down, and then the H over to the right. So you can see that like this over to the right. So then if I click on this other one, I get the other version of that. And if I put that, twist it around to be in the exact same position, now you can see that the OH is coming out toward us and the CN is going back away from us. Okay, back to this one again to compare. See, the CN is coming out and the OH is going back. There's no way to get those flipped unless we actually flip the entire molecule over, and that puts this chain in a different position now. But if we keep everything else in the same in the same way, in the same position, then those will always be in opposite orientations, one coming out and one going back in the opposite way. So that's what makes those two different. So see if you can play with that and kind of help yourself convince yourself. There are some good animations and videos on YouTube also that you can look up, and just look up chirality examples, and you'll see some nice models and some nice three-dimensional representations of that. All right. So there are a couple. So there are some new terms here. Let's refresh our memory with those. We've got chiral, a chiral object. Chiral does not necessarily apply to a molecule. It can apply to any object that has a non-superimposable mirror images. Yes, the dashed lines are going back behind the screen. So any shape like a hand that its mirror image is not the same as itself is chiral. And anything that its mirror image is the same as itself is achiral. So you see this example above me, this bottle. I think it's a bottle. You can see that the mirror image of the bottle is the same bottle. There's no difference. So it's the same thing. So that makes it achiral. All right. If we then apply that to molecules, chiral molecules have what are called stereoisomers, which are molecules that differ only by this kind of three-dimensional orientation, even though they have the same formula and they're connected the same. So they're kind of in between the isomers that we looked at before, which we might call constitutional or structural isomers, and actually identical same things. There's another one in the middle now that's stereoisomers, where they're connected the same, but they're still different because of this three-dimensional orientation. And then the last term is enantiomers. Enantiomers are two molecules that are mirror images of each other and are non-superimposable. So the example here would be these two molecules. These two molecules, A and B. A and B are stereoisomers of each other, but they are also enantiomers because they are exact mirror images, but they are not the same. So two molecules that are exact mirror images but not the same are enantiomers. Another way of thinking about that, besides the mirror image thing, which can sometimes be confusing with larger molecules, is this example up here on this website. If the dashes and wedges are flipped when everything else in the molecule is the same, then you have enantiomers. So enantiomers will always have opposite dashes and wedges, assuming everything else is in the same position. All right. So let's go down here and look at some examples and try to decide, are these molecules the same? Are they identical? Or are they enantiomers? So to be enantiomers, remember, they have to have all the same stuff connected, which I think all of these do anyway. And then what we're going to do is try to put, we'll go over them in a couple different ways. So first, let's take a look at this first group. And we want to know, are these identical or are they enantiomers? So the first problem here is, even though these are drawn as though they were mirror images, they aren't. If we draw like a line here and we kind of reflect this, we can see that doesn't really match up. These are not mirror images right now. That doesn't tell us the answer to this question. That just tells us this is not in a position that we can really make that distinction easily right now. So what we can do is, and what I would do with any of these, is I would flip, we need to rotate this molecule around in such a way that we can really compare them and see if they are the same, see if they are superimposable. So we notice here that the Cl is in the same, or the CH3 is in the same spot. It's on the top for both of these. So that's a good start. What we want to do now is kind of twist around that bond to put everything else in the same position. So instead of the Cl being on opposite sides, we want to kind of twist it around to put it in the same side. So I'm going to move the Cl around this way. I'm going to rotate everything around by a couple spots here. And let's draw the result of that. If I just this one on the right, I'm going to rotate this around so that the CH3 is still on the top and the Cl is over on the left. And then I need to think about what's happening to the rest of these, or to the other two, when I do that. So if the H is coming out, coming toward you, and we're rotating it around 180 degrees, where's it going to end up? Well, it's going to end up pointing back. So the H ends up back here, and that's the dashed bond. And then the OH, same idea. It's coming out at you, and we're rotating it around. So if we rotate around 180 degrees, that's going to put it back. That's going to put it out in front. The OH is going back right now. Sorry. If we rotate it, it's going to be going out in front. So that's a wedge. So now that we've done that 180 degree rotation around that CC bond here, or we can really just say we rotate the entire molecule around. Now we can see that these are actually identical. Everything is in the exact same position. And so that makes these identical. We rotate it around, we put two of them in the same position, and therefore we can see they're identical. Yeah, so those are identical. Okay, let's try the same one with this next one. Same thing with this next one. Again, the OHs are in the right spot. The bromines are opposite each other. So we want to rotate this around and see if they're identical or not. So we're going to do the same thing. Rotate this around 180 degrees. And that means that the OH stays on top. The Br flips over to the left. The wedged CH3 ends up in the back. And the dashed hydrogen ends up in the front. Now we're going to compare this one to this one. And we can see the OHs line up, the BRs line up, but the H and the CH3 end up being flipped. So that tells us that these are actually enantiomers. Right. And then I'll let you try the next two. We can come back and talk about them next time. All right, let's look at some other examples and some ways that we classify things as either isomers, stereoisomers, structural isomers, or the same thing. So here's a new type of yes, it's also a stereoisomer. So the reason that we have two terms, stereoisomer and enantiomer, we haven't talked about that yet, but there are stereoisomers that are not enantiomers. So here's an example. The double bonds don't rotate. Double bonds are fixed in place. They don't rotate. So that means that these two molecules are actually different because we can't twist that double bond to put the CH3 up here. So it's kind of stuck. So even though these are both examples where we have a 4-carbon chain with a double bond between the middle two carbons, everything structurally is the same, but they're not the same molecule. We can't interconvert between them by just rotating bonds. So these are actually different molecules. And that makes them isomers. But the type of isomer, they're not structural isomers, as we just said, because everything's connected in the same way. It's CH3, CH, CH, CH3, with nothing else branching off. So they're not structural isomers. And they're also not enantiomers because they're not chiral. Because the reason for that is they're not, well, there's a couple of reasons, but they're not mirror images. They're not chiral. They're not mirror images. In fact, if we took the mirror image of one of these, if we drew it, we would be able to superimpose it back on itself. So there's not chirality here. We don't have that situation where we have 4 different groups attached to a carbon because these double bonded carbons only have 3 groups attached. They're flat. So they're not enantiomers, they're not mirror images, and yet they're still stereoisomers of some sort. So these have a different name, and that name is diastereomers. So enantiomers are mirror images that are not superimposable. Diastereomers are other kinds of stereoisomers that are not exact mirror images. So other kinds of stereoisomers. And we'll see some more examples of this when we get more into the carbohydrates, because this is really what makes carbohydrates different from each other. All right, so moving down the list, the second one here, these are not the same. But now we have that kind of older, what we talked about before, we have structural isomers. So in this case, we have a line of 5 carbons with their hydrogens, so CH3, CH2, 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 CH3. This one, CH3, CH2, CH3, and then another CH3 over here. So they're connected in a totally different way. And that makes them not stereoisomers, but structural isomers, or constitutional isomers is sometimes the word used for that. How they're connected is different in that one. All right. I'll let you take a look at some of these other ones. Note with this last one, there are some names given here. You can see if you can figure out what those mean. We didn't talk about specific naming conventions of these things and how to write those names this semester, so you can look those up if you're not sure. That's not something you're expected to know. All right, so let's get into carbohydrates and apply this idea of stereoisomerism to these molecules. All right, most of this information you can find if you look stuff up. We're going to separate carbohydrates into 3 broad categories: monosaccharides, disaccharides, and polysaccharides. So the smallest type of carbohydrates are the monosaccharides, which is one molecule, one small molecule of somewhere between 3 and 6 carbons generally. And some examples you might have heard of: fructose, glucose, galactose. We'll look at some of those structures. Monosaccharides have a general form. This is where the word carbohydrate comes from. If you take carbon and water, and you have equal numbers of carbon and water, you end up with formulas like C6H12O6, which is glucose, and several other sugars have that same formula. And so that's carbo and hydrate. So that's where that word comes from. And so the monosaccharides are these different types of molecules that all have that type of formula. And we'll look at what those structures look like in a minute. Those monosaccharides can link up with others, and we'll talk about what that looks like, and form what we call disaccharides. So 2 sugar molecules linked together are a disaccharide, and then greater than 2 we call polysaccharides, where you start having these really, really big chains of monosaccharides, of molecules. So some examples here are given. You can look up what these are for, but monosaccharides like fructose, glucose, galactose; disaccharides, maltose, lactose; sucrose, which is table sugar, is a disaccharide of glucose and fructose. And then the polysaccharides are what we call starches or cellulose, things like that: glycogen, amylose, amylopectin, cellulose, glycogen. Those are all examples of polysaccharides. So lots and lots of these molecules hooked together. Starches can be broken. We break those down pretty easily in our digestive system. Amylose and amylopectin, they're kind of these branched chains of glucose molecules. Cellulose is glucose that's linked in a particular way that hydrogen bonds really strongly together and makes it unable for us to really digest it. So things like wood, plant structures, plant fibers, stuff like that, that's cellulose. All right, so here's a way that we often write, or you often see structures of carbohydrates drawn, kind of above my head here. And it's a little bit different. It kind of looks similar, but it's a special type of a way of writing structures called a Fischer projection. Fischer projection. And the difference between a Fischer projection and a standard structure or a Lewis structure is that it actually matters which side of this midline you put the two things. So it's a way of expressing stereochemistry. And honestly, it's a little bit of a confusing and difficult way to think about stereochemistry when we try to convert it to other structure types. We're not going to do that in this class, but if you want to look at where Fischer projections come from, how they're arranged, you can do that. We're not going to interconvert between the different types. Just it's a little bit beyond this class. If you take a biochem class or organic chemistry class, you'll do more of that. But just enough to know now that when something is laid out in this Fischer projection, and you really only see them with carbohydrates and sometimes amino acids, when they're laid out in this Fischer projection, it's not like a normal Lewis structure that you can just twist and turn however you want. You have to actually leave it in that specific configuration. The top and the bottom have to stay the same. And then when those are all laid out, it actually makes distinguishing different structures a little bit easier. So let's kind of dig in to some of these Fischer projections here. Monosaccharides are classified in a couple ways. So one way is by their functional group. So if it's CHO, we know, or you can probably guess, is not this. We know that because hydrogen can't have two bonds. So it can't be that. So CHO is actually a shorthand for an aldehyde functional group where the H and the O are both connected to the carbon. So that's an aldehyde, if you remember from the last chapter. And an aldehyde, being at the top of the chain here, makes that sugar an aldose. So this ose suffix is often applied to carbohydrates. That's why, like, they all have that, right? Glucose, lactose, sucrose, cellulose. Pretty much all of them have that ose suffix. And so if you have an aldehyde in your sugar, that's called an aldose. If instead you have something like this is now called a ketose. And you can probably guess that's because this is now a ketone. So the carbon atoms aren't shown here, but we're assuming, just like with the line structures, that there is one there. And this makes this thing a ketone and therefore a ketose. The other way that sugars are classified is by the number of carbons. So this one on the left has 1, 2, 3, 4, 5 carbons. This one on the right also has 1, 2, 3, 4, 5, 6 carbons, not also. So this one has 5 carbons, this one has 6 carbons. So this one could also be called an aldopentose for having 5 carbons. And this one could be called a ketohexose for having a ketone and 6 carbons. You get that? Ald from aldehyde, ket from ketone, and then pent from 5 carbons, and hex from 6 carbons. So aldopentose, ketohexose. And then, of course, all of these have their own names too, like glucose, ribose, whatever. You don't have to know all those names. We'll see how they differ in a second. And then the last way that we're going to classify them is stereochemically. So I said earlier that it matters which side of the line these OHs and Hs are, because if we can convert this to a chain structure, you would use actually different dashes and wedges for that. So that ends up being different stereoisomers. And sugars are classified based on the stereochemistry of their bottom OH group, their bottom chiral carbon in the Fischer projection. So the very bottom carbon, the one with the CH2OH, is not chiral because it has two H's connected to it. And remember we said earlier that if you have the same, if you have two of the same things connected to a carbon, it's not chiral anymore because you can superimpose its mirror image. This carbon up here has those four different groups attached. So we consider this a group, then OH, H, and then this thing is different. So that's four groups. So that's chiral. That's a chiral carbon. And in fact, the way these projections are laid out, all of the carbons that have these crosses here are chiral carbons. They're stereocenters. They're carbons that have four different things attached. So if we look at the bottom one, if the OH is over on the left, we call that an L sugar. And if it's on the right, we call it D. D or L comes from the words levorotatory and dextrorotatory, which has to do with how the chiral substance messes with light. You can actually take polarized light and rotate it in one direction or the other. That's how you can experimentally determine this. You don't have to know that necessarily, but you should know that L means this one's on the left, and D means this one's on the right. And so that's how we can classify these sugars. And because stereoisomers are actually different molecules, this actually really matters. And pretty much all biological sugars are D sugars. And the L ones would actually kind of mess with you in many cases, and not great. So, so to sum all that up, we can talk about the functional group, we can talk about the number of carbons, and we can talk about the absolute stereochemistry, L or D, based only on that bottom carbon's stereochemistry. So whether the OH is on the left or the right. Excuse me. All right. So let's find some actual sugars. Are they in here? I'm going to have to find another picture of this because I can't totally draw it. Oh, shoot. Sorry. Something. Open the wrong thing. Just a second. Almost there. All right. Here we go. Okay. So here are some examples of some different, these are all aldohexoses. So these are aldehyde sugars with 6 carbons. And you'll notice they're all D. They all have the OH, the bottom OH over on the right. But they all have different names. And their names all are related to the position of the other OHs. So allose, altros, glucose, mannose, gulose, idose, galactose, and talose or talose. The only thing that differs about these is the stereochemistry of the other OH group. So notice these are all D sugars, so the bottom OH always stays on the right. But then depending on where the other ones are, they become these different sugars. And so the only thing that differs among them is the stereochemistry. And these are actually all diastereomers of each other. They're not mirror images. They are just differing among the other stereochemistry. So they have some different three-dimensional orientation here. And as I mentioned, you don't have to memorize these names. If you go on and do more biochemistry, you'll probably need to know that stuff, and like which ones are which and which structures are which. But for now, just know that that they are, in fact, there are these differences based on stereochemistry. Okay, let me get some. Before we get on into the bonding stuff together, let's talk a little bit about those structures. Sorry, is anybody asking questions? No, okay. Just wanted to make sure I wasn't missing anything. All right, so let's take a look at glucose, D-glucose to be specific. So we've got our aldehyde. There we go. We've got our aldehyde on top and this CH2OH at the bottom. And then there's going to be 4 stereo centers, stereochemical carbons there. Hold on, I think I have that flipped actually. No, that's right. All right, so this is D-glucose. Again, you don't have to know that from memory, that's D-glucose. I'm just telling you that it is. Now, there's no real systematic way of getting all the other sugars from this. But what we do know is because of what we learned about stereochemistry, the D and the L sugars are enantiomers. So if we wanted to write L-glucose, which is the enantiomer of D-glucose, so those are enantiomers of each other. Remember that the enantiomer is the mirror image. And when we did all that mirror imaging of those single carbon molecules above earlier, what we found was that the enantiomers always flipped the dashes and wedges. They flipped all the stereochemistry. So if you know the chemistry, or you know the stereochemical configurations of the D sugar, you can also get the L one by flipping everything. So let me show you what that looks like. We still have our CHO on top and our CH2OH on the bottom. But what happens with the L-glucose is all of the stereochemistry gets flipped. So notice how I'm drawing these in the exact opposite way to make the L sugar. So that's the enantiomer. The reason I do this separately is a common mistake is because we know that the bottom carbon here, the bottom stereo center, gives us our D or L. Sometimes there's a temptation to just switch the bottom one if we want to draw the L sugar. But we have to recognize that the L sugar is the complete enantiomer, or the complete mirror image of the D sugar, and so actually all of it needs to be flipped to do that. All right, everybody with me so far? Maybe? Okay, the next thing I want to talk about is forming these ring structures called pyranoses and furanoses. We're not going to get into this too much, but I do want to show it just so the next part makes sense. So let's take our glucose, again, our D-glucose. And we've been writing all these things in this Fischer projection format, and I said, okay, this is with sugars. But actually, when you look up structures of sugars, you often see them in a totally different form. So like if we look down here, all of a sudden, glucose is being shown as a ring, as the 6-membered ring instead of the chain. And there's not really any explanation here. I think we took that out because when we change the some of the objectives. But what's happening here is naturally in solution, this straight chain structure is actually a little bit less stable. This is not the most stable form that this glucose can be in. Instead, what happens is this oxygen can reach around and link up to the carbon. So because it's a six-membered chain approximately, it can kind of bite back on itself and form its own ring. And if we count up the numbers of atoms in there, 1, 2, 3, 4, 5, 6, and the sixth one is an oxygen, that actually makes a six-membered ring, so a hexagon, or what's called a pyranose, Pyranose for sugars. Again, you don't have to know that term, but it ends up looking like this. So we often will see sugars drawn in this ring type structure. If we rewrite those numbers, so that oxygen was 6, it connected to carbon number 1, which is now over here, and then 2, 3, 4, and 5. So that's how these things work out. And it actually, you can figure out which some of the carbons, or some of the numbered carbons here, have certain parts kind of pointing up and other parts pointing down. That's how we identify the stereochemistry for these ring structures. Again, if you go on and take more chemistry, you'll learn precisely how to do that and how to take this structure and put it into this form. That's a little bit beyond what we're going to do. I just want to let you know that that is a thing that happens, and you can see some better pictures of it in the linked book parts. So just be aware that that is happening. So when we look at monosaccharides coming together to make disaccharides and polysaccharides, we need to just recognize that it's that ring form that's going to be used. And again, going back to last week's or a couple weeks ago stuff, the way that those things link together is through a dehydration reaction. So remember, we did dehydration or condensation reactions for carboxylic acids to make esters and amides. We do the same thing with saccharides. We bring two monosaccharides together, get rid of water, and then link together what's left to form the disaccharide. So if you take two glucose molecules and link them in a particular way, then we get maltose. So we can draw that. Remember, just like with the other organic reactions we learned last time, we don't want to change too much. We don't want to change anything except exactly what's happening in that particular reaction. So we're going to get rid of water and then link up the oxygen to this other carbon here. Sorry, I'm getting a little messy over here. Let me redo that. So everything else stays the same. And just to not be too confusing, we're not including any stereochemistry here. We're just drawing these things flat. But in the real structures, it would matter whether the OHs were on dashes or wedges. That would give us different compounds. So we hook those things together through this oxygen at this particular way, through a dehydration reaction, and that makes a disaccharide. That particular linkage is called a glycoside bond. And that's the way that sugars hook together. Right? So if you keep doing that over and over and over again, you can have 250 to 4,000 times, you have amylose, you have a starch. And that's now a polysaccharide. So you just keep doing this over and over and over and over again, and it kind of makes these big, long starch chains. And then depending on how those are linked and the angles of those things, that's how you have different types of polysaccharides, because they're actually all pretty much made of glucose. But the starch bonds, amylose, are made in one way that gives it a particular geometry, whereas cellulose has a little bit different geometry that allows it to hydrogen bond together really strongly. And that's why we can digest starches, but we can't digest cellulose because of how strongly the hydrogen bonding is. Now, when we digest these things, we have acids in our stomach and then enzymes in our body that can break apart these glycoside linkages. They can't for cellulose. You need multiple stomachs like a cow to do that. But we can break apart starches. So that's why when people say things like, starch is really just another way of like eating sugar, that's kind of what they mean, is that when these things break down, you're making monosaccharides, you're making glucose out of those, and so you end up having glucose as if you were consuming glucose. The kinetics and the way that works in the body is not identical, but that's why people say like, eating some pasta or bread or something is just like eating sugar. It's not exactly, but that's why, because it's made of those sugars, and then when it gets in the body, it's broken down similarly. So those are the main things to know about carbohydrates. In terms of what you need to be able to do, I just want to check, make sure I'm saying the right things. From Blackboard, the objectives are listed at the top of the learning module there. So we can get into a lot of fancy stuff with carbohydrates and their structures. But what we really want to focus on, identifying mono, di, and polysaccharides, defining chirality, and enantiomer, and stereoisomer. So what do those things mean, and what are some examples of them? The D and L forms of the sugars, and then hydrolysis and dehydration reactions. So we did a dehydration or condensation up here. And just as with the reactions we learned last time, hydrolysis is the opposite. So if you break this apart and then add water to regain the two glucose molecules, that's called hydrolysis, just like it was before with the other types of functional groups. And we'll see condensation and hydrolysis again even more with lipids, which we'll get into on Thursday. All right, so are there any questions about carbohydrates or any of this stuff? All right, well, let me know if anything else comes up. And otherwise, I'll see you on Thursday. So thanks, everybody. Have a good one.